Section 13.6 is on rank correlation. And the rank correlation test, or Spearman's rank correlation test, is a non-parametric test using ranks of sample data consisting of matched pairs. It is used to test for an association between two variables. R sub s denotes the rank correlation coefficient, and this was founded by Charles Spearman, born in 1863, died in 1945, called Spearman's rank correlation coefficient. The notation we're going to use is R sub s is the rank correlation coefficient for sample pair data. Rho sub s is the rank correlation coefficient for all the population data. N is the number of pairs of sample data, and D is the difference between ranks for the two values within an individual pair. The rank correlation, the hypothesis test that we could run, the null hypothesis is that the population Spearman rank correlation coefficient is equal to 0, so there is no correlation. The alternative is that correlation is not 0, so there is a correlation. The requirements are that the paired data are a simple random sample, the data are ranks or can be converted to ranks. The test statistic is one of, depending on which way you want to look at it, one of these two complex looking formulas. R sub s is equal to n times the sum of x times y minus the sum of x times the sum of y, divided by the square root of n times the sum of x squared minus sum of x squared times the square root of n times the sum of y squared minus the sum of y squared. We could also write this as 1 minus 6 times the sum of d squared divided by n times n squared minus 1. We could calculate this in SAS for Spearman's rank correlation, and the critical values if n is less than or equal to 30, use table A9. If n is greater than 30, use the following: R sub s is equal to plus or minus x divided by the square root of n minus 1. And kind of a flow chart here to go by. Are the pairs of data in the form of ranks? If it's a no, we want to convert the data of the first sample to ranks from 1 to n, and then do the same for the second sample. And then, does either variable have ties among its ranks? If that's a no, we want to calculate the difference d in each pair of ranks by subtracting the lower rank from the higher rank, square each difference d, and then find the sum of those squares to get the sum of d squared, and then compute the computation of R sub s is equal to the special formula to get the test statistic. Otherwise, we're using this other complex formula. If n is less than or equal to 30, we find the negative and the positive critical values of R sub s from table A9, and then run our hypothesis test. Otherwise, we use R sub s is equal to plus or minus z divided by the square root of n minus 1. R sub s, if R sub s is between the negative and positive critical values, we fail to reject the null hypothesis. Otherwise, we reject the null hypothesis. And the advantages to the rank correlation are that rank correlation can be used with pair data that are ranks or can be converted to ranks. This method does not require a normal distribution for any population. The rank correlation can be used to detect some, not all, relationships that are not linear. Its disadvantage, though, is its efficiency. Its efficiency rating is 0.91, which shows a minor disadvantage when compared to a strict parametric approach, meaning the Pearson correlation coefficient. So, for example, the experiment involves a growing population of bacteria. The table down here lists randomly selected times and hours after the experiment is begun and the number of bacteria present is counted. This uses a 5% significance level to test the claim that there is a correlation between the time and population size. And I already put that into SAS in here, exactly as this first table up here. Let me very quickly note what that is, this particular table. And then the program we're going to run for this is proc core data is equal to, I call this work.bacteria, Spearman, and then I put plots equals scatter and then run. Alright, this will give us a whole bunch of information, but it gives us down here, since, and did I not specify Spearman? I did, but that for whatever reason calculated the other one too. Well, if yours accidentally calculates the Pearson one as well, feel free to ignore that one. The one that we want down here, the Spearman rank correlation coefficient, this gives us a value of 1 and a probability of less than 0.0001. We could tell from this scale plot down here, this is definitely not linear. Right, and if we look at the regular correlation coefficient, notice how small, how this one has a value of 0.62092. So, widely different. But that's besides the point. For all intents and purposes, however, we just care about the Spearman correlation coefficient. So, for this, the requirements of this is that we have a simple random sample, and we could convert this into ranks if we wanted to, right? Which you could see was done so in this table down here. So because of that, we could do this. The null hypothesis is that the correlation coefficient, the Spearman correlation coefficient, is equal to 0. The alternative is that it's not equal to 0. Or, to say it different ways, no correlation and correlation. Right? So, the value that we get is R sub S. This gave us a value of 1 in our case, with the p-value less than 0.0001. So just to write this conclusion out then in English, at the 5% level of significance, we have sufficient evidence to claim that the that there is a correlation between time and bacteria population size, according to our test here, of course. The second example that I have is referring to the measured systolic and diastolic blood pressure requirements of 147 randomly selected females in the dataset 1 body data dataset, and used a 5% significance level to test the claim that among women there is a correlation between systolic blood pressure and diastolic blood pressure. Before continuing on with this, we could definitely say that this is a simple random sample. And the second thing we could say is we could definitely convert this into ranks if we wanted to. The null hypothesis is that this correlation, this Spearman rank correlation is equal to 0 for no correlation, and the alternative is that there is a correlation, so not equal to 0. I already have that data opened up on here. Since we only want the females though, we have to do a little bit of an edit to that data set. Since the regular body data set has both males and females. Male is coded as 1s in here. So to get just the females, we are going to use data, body data, we want to set the underscore temp2 period underscore 01 underscore body underscore data. If gender, this is an up, like an up sign, it's when you click on shift 8 equals 1. That just means we do not want gender to equal to 1 is what that does. Proc core data is equal to body data. Spearman var systolic and diastolic, and then run. There's a space between those two variables. When we do run it, and this time it only gives me the Spearman, which is exactly what we want, but it gives us some information up here. But it gives our rank correlation coefficient as 0.3541 with a p-value less than 0.0001. And we can look at the graph of that by including the plots is equal to scatter. Doing so will give us the graph of that, which looks like this, which is why this coefficient is kind of small on the smaller side due to the fact that there's not really any easily identifiable correlation between the two. But that's besides the point. So based upon the value that we got, we could say, and let me very quickly type this out, at the 5% level of significance, we have sufficient evidence since the p-value is less than 0.0001. We have sufficient evidence to support the claim that among women there is a correlation between systolic blood pressure and diastolic blood pressure. Let me know if you have any questions or concerns. Thank you.